Let's talk about trends. Now that we have a knowledge of the crystal field splitting for octahedral, square planar, and tetrahedral structures, now we get to see some interesting aspects of what happens when you have ligands such as water binding to your metal complexes. In the past, you've thought of dissolving salts in water simply by splitting the ions, right? You have your ionic salt with a cationic counterpart and an anionic counterpart, and upon dissolving them in water, you had cation and anions. But in reality, what you're actually forming is a set of coordination covalent complexes. The metal is coordinated by water, and the amount depends on the size of the ion, but usually you can get 6 water molecules bound to that metal center. And your anion is actually also interacting in a coordinative covalent fashion, either through hydrogen bonds or some other polar interactions. But you do have coordinated covalent bonds for the ions, and this is actually what the process of dissolution is all about. Okay, this is what we actually refer to as MX aqueous, right, or AQ. You're forming coordination covalent complexes. All right, so sticking with the octahedral pattern, right? You have 6 ligands around the metal center. We're going to be dealing with 2 orbitals at the bottom and 2 on top, with a negative 0.4 delta octahedral for the bottom orbitals and 0.6 delta octahedral energy values for the upper orbitals. Okay, so what I'm going to do is I'm going to show you what happens when you're dealing with certain transition metals. I'm going to focus on the 2+ transition metals. And the idea right here is that if we look at the picture starting with scandium and going all the way up to zinc, we're gonna develop a picture that's rather intriguing. Okay, first things first, one little shortcut that I need to tell you about is that the charge, granted, this is the charge of the complex, but it's all because the ligands are all neutral. Water has no charge, so the charge of the complex is the charge of the metal. But when you decide to determine how many d electrons you're dealing with in your metal, you have to determine the charge of the metal itself, which can be derived from the charge of the complex along with the charges of the ligands present, right? All ligands for the hexa aqua complexes are neutral, so the charge of the complex is the charge of the metal center. But be aware that you do need to get the metal center charge to do what I'm about to show you. So going with the 2+ charge for the metal, all you basically do is look at the group number for the transition metal and you subtract the charge of the metal from this group number. And this is how you will obtain the D count, the electron D count for each one of the metals. So scandium is in group 3. If we're going to look at the 2+ ion, then 3 minus 2 tells us that we're going to end up with a single d orbital electron in scandium. For titanium, if you do the same subtraction, 4 minus 2, we'll have 2d electrons. We'll have 3 for vanadium, 4 for chromium, 5 for manganese, 6 for iron, 7 for cobalt, 8 for nickel, 9 for copper, and 10 for zinc. And it's all based on the subtraction of the group number minus the charge of the metal, not the complex, but the metal. Alright, so let's see what happens. We're going to start with scandium. We only have 1 electron for scandium, so the only place we can locate and place that electron is in the bottom portion of the crystal field diagram. So we only have 1 electron present in the set of 3 d orbitals in the bottom. So that means that the energy, the delta octahedral splitting stabilization energy, is simply given by how many electrons we have in the negative 0.4 energy level and the +6 energy level. For scandium, we only have 1 electron in the negative 0.4 energy level and we have no other electrons, definitely no electrons in the 0.6 energy level. So the delta octahedral value is negative 0.4. Or in other words, you could say this stabilization energy for forming the octahedral complex out of the naked scandium 2+ ion is negative 0.4 delta octahedral values. Now the value of delta octahedral you do not know. This is a value that we will have to derive later on. In fact, I'll show you a table a little later that actually gives us those values. But for now, it's kind of like a reference point, but we don't know what it is in terms of the magnitude of the number. Alright, so we have negative zero point 0.4 for scandium, okay? So we're putting that number, that reference number right here for the delta octahedral stabilization energy. For titanium, we're dealing with 2 electrons, so we place the 2 electrons, one into each box of the bottom portion of the orbital set, and then we simply input the number of electrons that we have there. We multiply 2 times negative zero point 0.4. We have 0 on the upper ones, so we end up with a stabilization of negative 0.8. Vanadium with 3 electrons, we can place all 3 electrons on the bottom portion, and that means that we will multiply 3 by negative zero point 0.4, giving us a stabilization of negative 1.2. So what you can see here is that as we're going from scandium to vanadium, the stabilization of making the octahedral complex from the naked ion is getting larger and larger and larger. It's becoming more feasible and much more likely that you're going to form that octahedral complex. Okay, so let's take a look at chromium. Now, in the case of the aqua complexes, what happens is that you fill in electrons individually into each orbital first, and then you start pairing them up. I will talk about when the situation takes place in which you first pair up the electrons and then you fill up the electrons on top. But for chromium, we're going to place the 4th electron into the next empty box, which is now the DC square. So here we actually have 1 electron in the 0.6 energy level. We have 3 in the negative 0.4. So if we use the same equation, multiply 3 by negative 0.4 and 1 by 0.6, we're going to end up with a stabilization of negative 0.6 for chromium. And so what you can see now is that we're beginning to get a value that was more negative, and now we're becoming a little bit more positive. So it's not as stable for chromium as it was for vanadium. And moving on to manganese, which has 5 electrons, we will place the 5th electron on the next empty box. So now we have a total of 2 electrons on the 0.6 energy level, 3 on the negative 0.4. If you do the math, you're going to find out the stabilization energy ends up being equal to 0. So there is no stabilization by making the octahedral complex from the naked ion. You could make it, but you don't get any energy out of it. Moving on to iron, however, which has 6 electrons, now that we have filled in each box individually with an electron, the 6th one has no choice but to be paired up in the bottom energy level set, the negative 0.4 energy set. And so now we have 4 electrons on the bottom orbital. We still have 2 on the upper one. If you do the math, you'll find out that the stabilization energy ends up being negative 0.4. Moving on to cobalt, you add 1 more electron. Carry out the math and you find out that the stabilization energy is negative 0.8. Move on to nickel, which has 8 d electrons. Now we're going to add the 8th electron on the bottom portion. So now we have 6 on the bottom, 2 on top. We end up with a stabilization energy of negative 1.2. For copper, which has 9 electrons, we now have to place the 9th electron on the upper energy level. So now we have 3 on top, meaning that the stabilization is negative 0.6. And for zinc, that has 10 d electrons, we have 6 on the bottom, 4 on top. If you do the following multiplication and you add the numbers together, you'll find out that there is no stabilization energy. So what ends up basically looking like is that as far as forming the complexes, it becomes more stable until you get to vanadium. Then it starts getting raised up in energy, right? So now it's less stable. For manganese, there is not really any stability present. But then it starts becoming more negative, until you hit nickel, and then it starts going up again until you hit zinc. And the interesting feature about this particular double hump feature of the transition metal hexa-aqua complexes is that this matches up really well with the ionic radii of the 2 plus ions. So if you look at the 2 plus ions, so here is titanium 2 plus, vanadium 2 plus, so the superscript here represents the 2 plus charge of the metal. What you could see is a decrease in the atomic radius as you go from left to right, but by the time you get to chromium, the ionic radius goes up because the stabilization energy is not as negative. And when you get to manganese, you go up to the highest value because you have no stabilization energy present for manganese 2 plus. By the time you go to iron, now you have a more negative stabilization energy, so the ionic radius starts going down. And the same thing can be said for cobalt and nickel. This goes down in value, and by the time you get to copper, where the stabilization energy is not as negative, and then for zinc you have no stabilization energy, that's where you actually go up to a higher ionic radius and an even higher one for zinc. So the crystal field theory stabilization energy explanation is fantastic at explaining why the ionic radius of the transition metals doesn't follow the typical, decrease from left to right in the periodic table, and rather you have this double hump feature. It's all determined by the crystal field theory. So that's kind of phenomenal. I personally like that a lot. All right, so we're going to stop the video right here, and on the next video we're going to examine the actual energy values associated with the octahedral, tetrahedral, square planar complexes and the ligands which bind to these complexes.